Hey guys, today we are going to be doing section 1.3, and it's actually the easier of the 3 days. In 1.3 today we're just doing direct substitution, which is what you guys were wanting to do a couple days ago or 2 days ago when we were in class. So it's direct substitution, and here we go. Your classwork is going to be page 67, 5 through 37 odd. This is what I keep trying to warn you guys about. When we get into 1.3, it's going to require a lot of practice. So we're going to need to be doing a lot of problems. So try to keep up. Don't play catch up, play keep up. Okay, we're going to be finding limits using direct substitution, which is a lot easier than what we were doing before. When f of x is continuous, means no holes, no asymptotes, no broken up parts in the graph. When f of x is continuous at c, that's what we're looking for, you can simply substitute c in for x, and that's how you find the limit. So for an example, if we've got a graph over here, here's our f of x. See how it's continuous, no holes, no breaks. And I go and I want to find, here's my c value. I simply can look up, see what's going on there, and go over, and then my answer would be whatever that value is. Because it's continuous, we're going to be able to just take c and plug it into the function, and then that's what we're going to get. This would be f of c. Okay, when does direct substitution work? It works for all polynomial functions. Yay! When you have a rational function and c is actually in the domain, it'll work. So what do we have to look out for here? Whenever we have a fraction and it's got a 0 in the denominator, that is not going to work. We're not going to be able to do direct substitution. So that's why we're going to make sure that c is actually in the domain. Remember, how do we find that out? If we have numerator over denominator, I simply take the denominator, set it not equal to 0, and solve. Functions involving radicals with c in its domain. Again, we got to be careful. If we have a radical, what are we not allowed to have underneath there? We're not allowed to have negatives. That doesn't work. So what do? We take the radical, or with a radicand. Let's see. Can't squeeze it. We take the radicand and we set it greater than or equal to 0, and again, we solve whatever's underneath there. And you're going to find out if c is actually in the domain. Trig functions with c in its domain, what do we have to watch out for here? We have to watch out for asymptotes. Make sure that c is not an asymptote. So things like tangent, tangent has asymptotes, cosecant, secant, cotangent, those are all your ones with asymptotes. Secant, cosecant, tangent, cotangent. Those all have asymptotes at certain spots, depending on the period and the stretch and all that. Okay, here are your basic limits. For any real numbers, b and c, and positive integers, n. So no negative integers yet. It's positive. We're raising it to a positive power. So if I have the limit of b as x goes to c, then my answer is simply b. That means there's no x's. It's just a constant. It's just a number. So let's say I have the limit Okay, sorry about that. I'll go back and redo this example just to make sure you guys got this. I don't know where it stopped recording. Okay, so if we have the limit of b as x goes to c, then the limit itself is going to be that b value. There's no place to plug in c into the equation or into the function, therefore it's going to be simply whatever number is sitting there. So an example is limit of 3 as x goes to 2, that would equal 3. Okay, the limit of x as x goes to c, again, it's just plain old x. There's nothing else going on. So your answer is just going to be whatever number is there, and you plug it in. So for an example, the limit as x goes to, let's say, 4 of x, then our answer would be simply taking that and plugging it in, 4. Over here, the limit of x raised to the n is going to equal whatever c raised to the n is. That's what it means by direct substitution. You're taking the value here and you're substituting it directly into the problem. So here we would have the limit as x goes to, let's say, 5, x to the second. I would take 5 and plug it in. 5 squared is 25. Okay, let's talk about the properties of limits. For functions f and g, such that the limit of x as x goes to c of f of x and the limit of g of x as x goes to c, if it exists, then all of these properties are valid. And what do they mean? Well, here we have a scalar multiple. So if I take a number, let's say 3, and I multiply it the function f of x, that would be the same thing as taking the 3 on the outside. If the 3 was there times f of x, taking the 3 on the outside, and then finding the limit first, and then multiplying it by 3. Same with the sum or difference. I can either add f of x or subtract g of x first, then take the limit, or if it's easier, take the limit of f of x, take the limit of g of x, and then add or subtract them. All right, your product, same thing. I can either multiply first, then take the limit, or take the limit of each one and then multiply those. Quotient, I can take f of x divided by g of x and then take the limit, or I could do the limit of f of x over the limit of g of x. You just got to be careful. Remember, this cannot equal 0. It would be undefined. The power property, if I have the limit as x goes to c of the function f of x raised to the second, or raised to the n, I can do the limit of f of x and then raise it to n. So you can do either one. And then composite functions. I can either take g of x, plug it into f, and then find the limit, or I could take the limit of g of x first, take that answer, and then plug it into f, and then I'd be done. Okay, let's try some problems. All right, first example, we're going to evaluate the limits using direct substitutions. We just need to make sure C is in the domain. Again, it will work all day today. Tomorrow is where we're going to up the ante, and it's not going to be in the domain, and we're going to have to do some rewriting, which that's going to be where it gets a little confusing. Okay, the limit of 3 as x goes to 2. Well, there's no place to plug in the 2, so my answer is simply the the number sitting there, which is 3. The limit of x as x goes to -4, you take and you plug it into there, and my answer is -4. These are your basic properties. The limit of x squared as x goes to 2, that's part of the domain. 2 is in domain. I don't have a radical or a denominator, so I don't have to worry about those restrictions. So I take and put 2 in. 2 to the second power is equal to 4. That would be my answer. Okay, let's try the limit of 4x squared plus 3 as x goes to 2. 2 is in domain, so I'm good to go. So I just take him, plug him into the function, and then evaluate. 4 times 2 squared plus 3. 4 times 2 squared, so you get 2 squared first, which is 4. 4 times 4 is 16. 16 plus 3 is 19. Here, the limit as x goes to 1 for this function, x squared plus x plus 2 over x plus 1. This is a rational function, so I need to be careful of the denominator. I need to make sure 1 is in domain. And it is. What's the one number that's not in the domain? -1. So that's the one you'd have to be careful about. So today we only have 1. That means everywhere you see an x, I'm putting in a 1. So I've got 1 squared plus 1 plus 2 all over 1 plus 1. 1 squared is 1. 1 plus 1 is 2. 2 plus 2 is 4. 1 plus 1 is 2. So 4 divided by 2 is 2. The limit of x squared plus 4 for x goes to 0. Here we have to make sure that 0 is in the domain. And if I have any negative number, at x squared plus 4, I can put in a -2, and I would still get a positive number because I would get -2 squared, which is 4. 4 plus 4 is 8. So anything can be put into there because you're going to be squaring it and then adding it, so you're never going to get a negative number. Okay, so here I'm going to take 0 and plug it in. I get the square root of 0 squared plus 4, which is the square root of 4, which is 2. Okay, last row. The limit of tangent x for x goes to 0. We have plug in tangent at 0, which is equal to sine at 0 over, of course you can just plug this into your calculator, but this is a little bit more fun. Sine at 0 is 0. Cosine at 0 is 1. Think about your point right there. So we have 1, 0. That's your cosine, that's your sine. So sine at 0 is 0, cosine at 0 is 1. Our 0 is in the numerator, so we're okay. Our answer is 0. Okay, the limit of x times cosine x as x goes to pi. I'm going to plug pi into both of those. If you're going to be using your calculator for this, make sure you're in radian mode. So I get pi times cosine pi. I don't think you need your calculator. Pi is sitting right over here. It's -1, 0. I'm going over there. -1 is my cosine, so I have pi times -1, which equals -pi. Last, we have the limit of sine squared x as x goes to 0. And it's very important that you understand how you can rewrite this. This is not sine x times sine x. This is sine of x quantity squared. So the limit as x goes to 0, sine x squared. So here, oh, sorry, that would be sine x times sine x, but you want to write it like this so you can use the property, power property. So we can use this property right here. If you rewrite it, now all we have to do is find the limit of sine x, and then I can take that and square it. So we have x, 0 is going to go in the x spot. So sine of 0, quantity squared. Sine of 0, we showed you a few minutes ago over here. Here's our 1, 0, or here's our 0 point on the unit circle. Sine is equal to 0 itself, because it's our y value. So we get 0 squared, which is 0. Okay, hopefully those weren't so bad. Here is a try it. So you guys might want to go ahead and pause the video. You can pause and then try these 5 problems. I'm going to show you the answers in a few minutes, and then tomorrow in class, you guys can ask me anything. You can go over any of these. So here, go ahead and pause the video. Okay. Here are the answers. I'm not going to have the work shown. I just want you to go and check your answer. If you got an answer wrong, please make sure you ask me in class tomorrow. Ask me in class if you got one or more wrong. Please. Please, please, please. Please. Okay. All right. Oop, I wrote it there. You can't see it. All right, guys. I hope that wasn't so bad, and I'll see you in class tomorrow.